All right, so in the blockchains, our aim is to talk about elliptic curve digital signature algorithm. So in order to talk about it, let's talk about elliptic curves and elliptic curve cryptography. So here, elliptic curves are just geometric objects, and it can be defined like this formula, which is y squared equals to x cubed plus a times x plus b. So very simple geometric object. But depending on the choice of a and b, if you plot this elliptic curve in 2 dimensions, these are the things that you will observe. As you can see, sometimes it is a single piece like this. Sometimes it is 2 pieces like this. But regardless, most of them are, give us the same security. So, this choice actually depends on you. So there are many elliptic curves. Important thing is that the part that we are interested, actually, points on an elliptic curve generates a group where the points are the elements of the group, and the addition of 2 points P and Q is defined as the point as follows. You draw the line that passes through P and Q. Recall that only a single line can pass through 2 different points. It intersects the curve at a third point R. This is coming from the definition of the elliptic curve, actually. So multiply the y-coordinate of R with -1, and we claim that the resulting point is now P plus Q. So I will also show this on a picture to explain how it is done. We need an identity element to say it is a group, right? So here we defined how the binary operation works, how we add 2 points and obtain a new point. But now, in order it to be a group, this operation to be a group, this set, we need an identity element. So this actually again comes from geometry. We say that there is a point at infinity, which is actually at the top of y coordinate. So when you plot this in 2 dimensions, this might be, sounds strange because we are using affine coordinates. But in different coordinate system, this makes sense actually. So this is how we define the group elements. So assume that there is an identity element. So somewhere in the, infinity at positive y coordinates, right? So we think of this as if we go vertically upwards, we will reach that identity element at some point. So this is called the neutral element or identity element, and represented as O. So addition, let's talk about addition first, and we will talk about inverse. So addition of P and Q, as I explained above, just you draw the line through here. It has to intersect the curve at the third point. Just reflect it with respect to the x-axis, which means that you multiply the y-coordinate with -1. And we say that this is now P plus Q. A very different addition operation, but this creates a group at the end. And you might ask, what happens if I add the point P to itself? So then you draw the tangent line passing through P, then it intersects the curve at another point. Again, you reflect it. Now we call this 2P. So as you can see, now I have a method to add a point to itself. So if I add P to 2P, so if I draw a line through here, it has to intersect at some place here or here. So you reflect it and obtain 3P, 4P, and so on. Actually, this is the thing that we are going to use for the discrete logarithm problem. But to give a flavor, I told you that when you create a Bitcoin account, actually you randomly choose a number D. Then you add this point to itself D many times. So you end up with D times P. And that will be actually your public key. Of course, you will take the hash of it and so on. So these points on the elliptic curve will be our cryptocurrency wallet addresses. So this is why they are important for this course. Of course, since we defined the point at infinity as identity, the inverse element just becomes the, P to minus P is defined as just, reflecting it with respect to the x-axis, okay? This is minus P, because if you draw a line, this vertical line, it passes through here and passes through here and goes to infinity. So this is why we say that there's a point at infinity called the identity element. So these are actually the geometric definition of the group operations. Of course, when you want to add P to Q, you cannot just draw a line because, most probably you are writing a programming code. So you have to obtain this point from these 2 points just by looking at the XY coordinates of these 2 inputs. So you can obtain the output as the coordinates. So before showing those formulas, let me again show you the idea, what we use in practice, because if I use this elliptic curve in practice, which is drawn over real numbers, you will notice that there are infinitely many points here. But as I mentioned before, in practice, I want to represent these points as finite elements, so I have to limit these points to finitely many elements. So this is why instead of working over R, we work over something like Z89 in this picture. Of course, in practice, we need a lot more points, so we have to increase this number to a huge number. But to visualize, just consider the points on this elliptic curve whose coordinates are actually elements in Z89. So these are the remaining points. There may be 100 or a little bit more points here. So these addition operations and so on actually apply to these points too. Of course, in this case, you wouldn't plot a line because now we are no longer in the real axis, okay? So elliptic curve crypto systems were invented independently by Neil Copley and Victor Miller in 1985. And currently, there are many standards, and we are actually transitioning from RSA to elliptic curve cryptography because it is more secure, because the discrete logarithm problem on this group doesn't have a sub-exponential time algorithm. Okay, so let's move on to the definition of elliptic curves. Then I will give you the formulas for how you calculate addition. So consider elliptic curves over Fp. We already mentioned what a finite field is, right? So Fp is a finite field. So most standards which specify the elliptic curve cryptographic techniques restrict the order of the underlying finite field to be an odd prime, so Q equals to P, or a power of 2, Q equals to 2m. So in the standards, you will only see elliptic curves in this format, either a very large prime or a huge power of 2. So there, of course, you can have elliptic curves in different manners. For instance, instead of 2, you can choose another prime like 7. So you can have elliptic curves over, Q equals to the 7 to the power m. But this will mean that you can define many, many elliptic curves. But in the idea as a standard, you would like to, stick to just a few. This is why all of the standards only focus on these 2 cases. So let's focus on the first one. Assume that P is an odd prime larger than 3. Then we define an elliptic curve E over Fp as follows, as the equation y squared equals to x cubed plus ax plus b. Here, a and b now the elements in the field, but also this inequality should hold. In other words, 4a cubed plus 27b squared should be different than 0 modulo p, so that we can use it as an elliptic curve. This is actually how you choose an elliptic curve. Okay, whenever you choose a and b, you have to check if this inequality holds, because if it doesn't hold, then you will say that it is not an elliptic curve. All right, now let's look at the points on the elliptic curve. We define it as the set EFP. These consist of all points xy coordinates, x and y coordinates, where x element is in the field and y is also in the field, that satisfy this equation. Of course, we add the special point O, which is the point at infinity. So these are actually your points on the elliptic curve. Again, these will be your public key addresses when you use digital signatures, and they will turn into Bitcoin or Ethereum account numbers at the end. So let me give a basic example to visualize how this works. So I choose R prime as a very small number like 23, and consider the elliptic curve y squared equals to x cubed plus x plus 4. So as you can see, I chose A here as 1 and B here as 4. So first check if this is an elliptic curve, right? I said that we have to check if 4aq plus 27b squared is different than 0 modulo p. In our case, modulo is 23, and this number is different than 0. Yes, E is indeed an elliptic curve. So now let's look at the points on this elliptic curve. So you can actually, since this number is small, you can try one by one. We said that we are looking at the coordinates x and y where they are inside the field. So just for instance, in this equation, let's choose x equals to 0, right? When x equals to 0, these cancel. So you end up with y squared equals to 4. So this means that 2 is an element in this field which satisfies y squared equals to 4. But also minus 2 also will give you 4. But minus 2 is not in this field, right? Because there is no element as minus 2. But we have instead 21. Because you add minus 2 to r prime here and end up with 21. So when you choose x equals to 0, you end up with 2 points on this elliptic curve. If you choose x equals to 1, you observe that y equals to 11 and 12 satisfy this equation. But when you choose x equals to 2, if you write x equals to 2 here, you will realize that there is no y in this field that satisfies this equality. So this way, you can write everything and you end up with 28 points, but plus the point at infinity, so you have 29 points. Of course, in order to use something like this for a Bitcoin, I cannot use this because 29 points, or if you remove the identity, 28 points means that you can at most have 28 different wallet addresses, right? Which would be impractical, right? We cannot use it. So this is why we have to choose this P as a very large prime, so that we have virtually infinite many wallet addresses, so that people can instantly create new wallet address and so on. So now this also leads us to the question. Here I actually obtained these points one by one by trial and error, putting x equals to 2, 0, 1, 2, and so on. So if P is really large, you cannot do it by hand, right? Such a brute force will be very hard to calculate. So it will be actually an exponential time algorithm. So we should need fast algorithms so that whenever I choose an A and B for the definition of the elliptic curve, and when I choose a very large prime, that algorithm should give me the number of points on this curve in a very fast way. Good thing is that we have an algorithm from 1985 by Skoof. So he presented a polynomial time algorithm for computing the number of points on an elliptic curve over the field FQ. So the number of points on an elliptic curve over FQ indicates when Q is odd. So this paper actually only works for this case, but Koblis extended it to the case where Q equals to 2 to the n. But of course, these algorithms are polynomial time, but still inefficient because in practice, Q is really large, right? So there are many optimizations, there are many algorithms. So currently they are called as C algorithms due to the works of Skoof, Alkes, and Atkin. So it received many improvements, but at the end, we can create such an elliptic curve which will be suitable for our needs in a few hours. So we can easily come up with new elliptic curves. Okay. Let me show you the group operations again, but because initially I explained it as in a geometric way. Now let me explain it more mathematically. So identity element gives you the same point. So there's a point at infinity. So we can also see it from the picture. Here is your point P. So if you add the identity element at infinity, you draw the line from the infinity to P, so it will intersect at this point. You reflect it with respect to x coordinates, so you end up with the same point. This is why P plus identity element, the point at infinity, gives you the same point. Now, let's talk about how we add 2 points. So we said that if P is xy, is that you simply, multiply the y coordinate with minus y, then you obtain minus p, because if you add these two, you end up with identity element, the point at infinity. Anyway, the more important part, how I can add 2 points without, geometrically drawing a line and so on. So let P and Q be 2 different points, okay? And P has the coordinate x1, y1 over Fp, and Q has the coordinates x2, y2. Again, these are elements in the finite field. So the resulting point P plus Q, which will have the coordinates x3, y3, are calculated as follows. x3 equals to y2 minus y1 divided by x2 minus x1 squared minus x1 and x2. Similarly, y3 coordinate is calculated like this. Here, but of course, you use x3, so first you have to calculate this one, put the result here. So here, one important thing is as follows. We have minus and division here, but we are working on the fields. So by division here, we are actually talking about, multiplication with the inverse element and so on. So don't forget that these operations are field operations. So another question, what happens if I add P to itself? Right? How can I calculate 2P? Because in this example, we had P and Q, 2 different coordinates, but now I want to add P to itself. So I have only x1 and y1. So the resulting point 2P, which is x3 and y3, is calculated again in a similar formula without having, x2 and y2s. We have these values here. Okay. So this is how it works. So this is the mathematical formulas for the geometric explanation. So it is a very nice practice, and I encourage you to implement these just without using any libraries, just using choosing a small p here, the field prime, and implement this. It's a very nice exercise. So let me again give an example. So I choose the same elliptic curve that we used before, F2 over F2 and 3. Since the number of elements on this elliptic curve is 29, which is prime, this means that actually this elliptic curve is cyclic, and any point other than the point at infinity is actually a generator. So this is actually, as you can imagine, is coming from a few theorems. You cannot see this by just looking at it, but this is just what I claim, so just take it for granted. So let's choose a point then, 0, 2. So let this be my point P. If I want to calculate 2P, I have to go back to this definition, perform this operation. So if you do that, you obtain this point. Now I want to calculate 3P. So now I need to add this point to this point. Again, using the formula, this time using this one, because P and 2P are 2 different points, you end up with 3P. So if you continue in this way, you will realize that at the end, you obtain the identity element here. So this point really generates all of the points. So P is a generator of this elliptic curve over the finite field F23. So again, this is a very nice exercise. I recommend you to do it. Okay, all this theory. So let's move on to Bitcoins, Ethereum and blockchain. So Bitcoin uses an elliptic curve, SECP 256K1. So this is actually not a NIST standard, but it is actually defined in the standards for efficient cryptography, SEC, from Certicom Research, and you can follow this link and download this PDF and see all of the defined elliptic curves, and Bitcoin chooses this one, and there's a reason for that. And the chosen elliptic curve is defined as follows: y squared equals to x cubed plus 7. As you can see, there is no x here. This means that a is chosen as 0, and this is 7, so this means that b is chosen as 7. So this is defined over a very large prime field, Fp. So P is chosen as follows. It's equals to 2 to the 256 minus these values. So the result actually gives you a prime number. All points on this curve, therefore, are valid Bitcoin public keys. If you represent P in hexadecimal, as you can see, there are many Fs and there are just a few different values. This is because if you fill it with all Fs, you will end up with 2 to the 256 minus 1, right? So these other values actually coming from these minus values. But the good thing is that this is a prime number. Base point G is defined as this, okay? So this is the X and the Y coordinate of the base point. So whenever you want to create a Bitcoin account, actually, you choose a random value D and add this point G to itself D many times. So the resulting point will be your public key. So order of n is, as you can see, different than this prime number. This is important because it doesn't generate, this many points, but it generates this many points. This is what it means. So at most, this many different Bitcoin wallet addresses you can create. But important thing is that since this is the used in Bitcoin and we had very efficient C implementation for this, following cryptocurrencies like Ethereum and any other alternative currencies actually use this elliptic curve and also use the same implementation. So this is important. So there are some misunderstandings because, for instance, I recently read a book which was published in 2008 about Bitcoins or cryptocurrency. And in the book, it says Bitcoin uses the SECP 256K1 curve defined by the National Institute of Standards and Technology, NIST. This is wrong. This is not defined by NIST. And actually, it wasn't a NIST standard for a very long time. And if you look at the internet, people will ask why Bitcoin uses this elliptic curve. And people will answer like Satoshi chose this elliptic curve for no particular reason. Actually, these are all wrong because Satoshi chose this because it is not a NIST curve. Okay. As I mentioned here, it is from Certicom. You can go to this PDF and see this elliptic curve. And you will realize that even in that document, it says that it is not standardized by NIST. Satoshi does this because in the past, NSA tried to weaken standards that are used all over the world. So this way, instead of choosing a NIST approved elliptic curve, Satoshi chooses something else deliberately. So her main idea was that this is not a NIST curve, so let's use it. But it is also a standard, and it is shown that it satisfies good cryptographic properties. So there are no known attacks, so let's use this one. So for a very long time, Bitcoin used an elliptic curve that is not used by NIST or many other people. So last year when I was teaching, I told you that I had an inside information around February 2022. Since this elliptic curve is now used in all of the cryptocurrencies, I said that NIST will include this elliptic curve in their documents just for interoperability. And this happened last month. So NIST published their new document, NIST SP 800-186. So this special publication actually removes digital signature algorithm, by the way. So it will no longer be used, which I also mentioned last year. So as you can see, Bitcoin's idea of using elliptic curves was a good thing because currently we stop using digital signature algorithm and people are moving on to elliptic curve digital signature algorithm. So NIST puts this elliptic curve in the appendix. So in the current version, finally, we have this elliptic curve defined in the NIST document. And NIST explained this decision as follows. While NIST does not believe that this elliptic curve offers compelling advantages over the NIST recommended curves in special publication 800-186, NIST acknowledges the significant use of this elliptic curve in these applications. NIST technical guidelines in this document will allow the use of this curve for blockchain and distributed ledger technologies related applications. So they added this because now the whole world is using it. So this is the main mathematical background that we need to understand digital signatures that we use in cryptocurrencies and blockchains.